Okay, so the idea here is that we want to be able to write down an approximation of the area under a curve for a general function, right? So suppose we have just a function that is defined on an interval a to b, and we want to approximate the area under f. And so suppose we want to use n rectangles. Okay. So if they each have equal width, which we usually suppose that they do, so if they each have equal width, then since we are approximating on this fixed interval, a to b, the width must be so we would just take our interval, the length of it, that would be b minus a, and we chop it up into n pieces, so we just divide it by n, and that will give us the width of each interval. So this is a useful formula to have, so just make a note of this. Right. Okay. Now, what we're going to do is figure out what the endpoints of the intervals are. So just to write these down, we don't have a graph of a function right now, but that's okay. We can still use the same process by first writing down the endpoints and then just choosing, say, the left-hand endpoint if we want to do a left-hand approximation, or the right-hand endpoint, or we don't even have to choose an endpoint. So we'll see in a second. So the endpoints of the intervals oops. Okay, it doesn't want to erase. The endpoints of the intervals are going to be, we will start with, so we're going to label them x0, x1, up to xn. X0 is going to be the end of the interval. So if we want to picture this, if we have our interval a to b, and we're going to chop it up into pieces, we're just labeling a as x0, that's our starting point. X1, we want to jump over by delta x, right? So I'll instead draw this as a line so we can see a little better. And so we want to jump by delta x to get x1, the next point, right? So x1 is equal to a plus delta x. To get to x2, we want to jump another delta x, right? So we want to jump by delta x again, and so that's going to be a plus 2 times delta x, and so on. We would just keep doing this to get each of the endpoints. So we got x1, x2. For an arbitrary endpoint, we usually use xi. Okay, so at some point in the middle, we're going to have xi, and that will be a plus I times delta x, right? And then we'll just keep going all the way until we get to the end, and we know that at the end it should be equal to b, right? So xn, which following this pattern will be equal to n times delta x. It should give us b, and if we work this out, knowing that delta x is equal to b minus a over n from our formula up there, we get b minus a over n. So these n's cancel, and we do get a plus b minus a. So those a's cancel, and we get b. So we do end here with xn equaling b. Okay, so these are each of our endpoints. And then looking back, so I'm just going to clean this up a little bit. Looking at our interval, and let's say just focus on the first interval, which is going to be from x0 to x1. I'm just going to use the label x0 just to be consistent. In this interval, we want to choose a point x1. Oh, sorry, x1 star. And this point is going to be the one that we evaluate the function at to get the height of our approximating rectangle. And so, like I said, it could be a left-hand endpoint, it could be a right-hand endpoint, but it could be something in the middle. So really, we're not going to specify what it should be. Oops. Okay, undo that. We're not going to specify what it should be. We're just going to say that we choose one in the rectangle. Okay, so that is just some point in here, so we'll call it xi star, and then we just continue this process for the other intervals. So in the interval x1 to x2, we're going to choose a point and call it x2 star, right? And so we're just going to keep doing this. So for, oops. Sure, we're going to pick, okay, for each integer I between 1 and n, we pick xi star in xi minus 1 to xi, right? Okay, now, okay, so I'm actually going to not use, I'm going to use this space to finish this derivation, and we'll do the example in class. Okay, so for each I between 1 and n, pick an xi in there. So what happens, let's say our function looks like this, and this is our interval from a to b, and we've chopped it up into pieces, right? And in each of those, we have picked a point, so I'm just gonna pick some random points around here, maybe a midpoint, maybe close to the end point, maybe the last one is the end point, something like this. And like I said, these are going to give us the height of our approximating rectangles. So it will look like this. Unfortunately, I didn't draw these so that the intervals are all actually the same width, but pretend that they are. So I'm just, from the point that I picked, I'm following it up to the curve, and wherever this line from the x-axis to the curve, wherever it hits it, then I draw the rectangle there. So this is really just the same process, but we're using random points in the interval instead of left-hand endpoints or right-hand endpoints. Wait, that one's... Okay, and so almost done with this. Okay, so here we get our approximation, right? This is what it would look like. Let me fix this to be consistent. There we go. Okay, now what we're going to do is write down what this area is equal to. So we're going to use A for the area under F. And so since this is an approximation, we will write that as an approximation. This is going to be just the sum of the areas of the rectangles. So starting with the first rectangle, we know that that starts with, let me label some of these points. So this is x1 star, x2 star, and so on. And then in here we get xi star, so we would just continue on labeling. Okay, and now remember that the width of each rectangle is exactly the same, so we are always going to get delta x as our width times the height of the rectangle, and the height is the function evaluated at that particular point, f of x1 in this case. And then we would get, for the next rectangle, delta x times f of x2 star, and then we would continue doing this for each I between 1 and n. Oops, I forgot my delta x. So right, and then we would stop when we get to the last interval, and we would get delta x times f of x n because we are at the end. And that is the sum of all of these orange rectangles that I drew. Okay. Now, even though I did draw a finite number of them because I, don't have, well, we're supposing that that n is arbitrary, so that's why I'm using xi for some random one in the middle, and then xn is the end. So I'm trying to not specify what n is going to be, right? Okay, now all we're going to do now, this is our area approximation. This is what we will call a Riemann sum, but we just want to write it using sigma notation, which is going to make it a little bit nicer. Okay, so each term has a delta x in it. So to simplify this, we can just pull that delta x out. I'm going to just switch back. And then we get a sum of f of x1 plus f of x, or x1 star, f of x2 star, f of xi star, and then all the way up to f of xn star, right? And we just are going to use our sigma notation to write down this sum. Okay, so delta x is out front. That's just a number, it's a constant, so we'll leave it out front. And then our summation, the thing that we're going to be summing is f of x star. So we get one of those for each I, and I starts at 1 and ends at n, so those are going to be our bounds, and that is what we are adding up. So that is how we write this with summation notation, right? Okay, now, so just to summarize, the area is approximately equal to delta x times the integral, the sum from I equals 1 to n, f of xi star. And like I said, we will be eventually, so this is usually the form that you see, the Riemann sum. And we will eventually be taking a limit as n goes to infinity, so we'll take more and more and more approximating rectangles and get an exact answer for the area. And just to point out, just to point out the delta x, just so this is a little bit more readable, is the width of the rectangles that you're using. And each of these is, so altogether, it's the sum of all of the heights. And if you just look at just one, f of xi star, that is the height of the ith rectangle. Okay. Right. So that is the Riemann sum. We'll do an example at the beginning of class of actually computing one of these, but for now, just complete the comprehension check question.